Okay, this is video number 9 in chapter 10. Boy, it's more than I thought we'd have, but it's a pretty important subject. So let me pick up where I left off. I was talking about the various shapes that are molecular shapes that are formed when the number of electron groups around the central atom varies between 2, 3, 4. I think I finished off with 4. I'm about to go on to 5. So let's talk about what happens when a central atom has 5 electron groups surrounding it. So first of all, this is actually one of these things which should set off a red flag, which is like, wait a minute, how can you have 5 electron groups around a central atom? That would end up with more than an octet. Okay, I want to talk about that first, maybe I mentioned this a bit already, but the reason, and I'll put up a sample compound, which is phosphorus pentafluoride. Okay. In fact, let's actually do the Lewis structure on this, and then from there I'll drop back into the shape argument. But I'm actually going to take this compound, phosphorus pentafluoride, and we'll do the Lewis structure evaluation on it. Okay. So phosphorus pentafluoride. Well, first we need to draw this. We'll start with the least electronegative atom, and we'll put that in the center. That's phosphorus. Okay. And then we've got 5 fluorines that we'll put around it. Is that 5? No, one more. Okay. All right. Now we have to do our our valence electron counts. So phosphorus has 5, right? And fluorine we've got 5 of them, so it's 5 times the number of valence electrons for fluorine, which is 7 each. So that's a total of 40 electrons. We're going to be busy here, aren't we? So I've drawn 5 of them to around the phosphorus already. Now let's draw in the fluorine. So each of the fluorines has 3 pairs. Okay. Quickly add it up. That's just looking at the lone pairs. We've got 6 on each fluorine. That makes 36 plus the bonds, which are 2, 4, 6, 8, 10. 30 plus 10 is 40. Boom, we're set. So this is our first attempt at the Lewis structure. Now let's evaluate in terms of octet. First of all the fluorines have an octet because they each have 3 lone pairs and then 1 bonding pair. So each of them has a full octet, so that's good. Phosphorus, though, has 2, 4, 6, 8, 10. That's right, it turns out. It's correct, although it sure looks odd, doesn't it? It's one of these violations to the octet rule. Okay, it's a valid violation, and here's why. I mentioned it once before, is that phosphorus, it is in period 3, and it has the structure of argon. I have room to show that. Let me make sure I got that right. Structure of neon, sorry. So phosphorus is neon, and a 3s has 2 electrons there, and it has a 3p, it has 3 electrons there. So that has its 5 electrons in phosphorus. Again, though, if you remember way back to the quantum mechanics, at the n equals 3 level, there's also d orbitals. That are possible. They're higher energy, which is why, remember, they don't even get filled until you get down into the 4th row of the periodic table. But they still exist, 3D, and they're just, there's none of them filled for phosphorus. But the orbitals do exist, which means that the electrons around phosphorus can actually fill not only the s's and the p's, but they can also actually spill into the d orbitals that exist for n equals 3. Okay. And that actually explains why groups that are at least in period 3 or higher, or further down in the periodic table, can have more than an octet. By the way, it would not be possible to have nitrogen tetrafluoride, even though nitrogen also has 5 valence electrons, but nitrogen is up at n equals 2 on the 2nd row of the periodic chart. There is no d orbital there, So this compound here is impossible, where it is actually not, it is very possible for phosphorus. And it would also be for, what's after phosphorus? Arsenic. So arsenic pentafluoride would also be possible because it's further lower in the periodic table, meaning it's at N equals 4. It's the next level down. Okay. All right. Now, so that was important, and then the exact same concept applies for the when you have a molecule that's attached to 6 different electron groups. And again, the same thing happens is, of course, the d orbitals have room for a lot, for 5 more pairs of electrons. So that's why it's possible to have 6, and even for that matter, it's theoretically possible to have even 7 and higher. Okay, now back to our shapes. So that was a departure to talk about why we had this this violation of the octet rule, going bigger. Okay, so from a shape standpoint, phosphorus pentafluoride has a shape which is called trigonal bipyramidal, and you can look in your book. This takes some getting used to memorize these shapes. It's kind of important, I think, to memorize these shapes, probably for your exam as well, because I can imagine some problems on your exam that will say, here's a compound, write the Lewis dot structure, and tell me what shape it is, and tell me if there's any effect on bond angles. That'll be a very common question that I think you'll definitely see. So in this case, the shape of phosphorus pentafluoride is trigonal bipyramidal. Okay, again, it's right out of your when you look at in your book on mine is in figure 10.7. It shows this exact example, phosphorus pentafluoride. Okay. Now I want to show though another example of the 5. Which one did I want to show? Yeah, the one I want to show next, which is still 5 electron groups but has a different shape, is sulfur tetrafluoride. Okay, sulfur tetrafluoride will actually look like this. And it has a lone pair. And if you look at this, here sulfur it violates the octet rule, but sulfur can because it's at period 3. So in this case, there are 5 electron groups around the central sulfur atom, the 4 for each fluoride, and then the lone pair around the sulfur. So this is one of these cases of 5. However, the molecular shape is not called trigonal bipyramidal because the molecular shape just looks at the atoms involved. And the atoms involved here, they call this shape seesaw. Very nice little technical term. Because it's kind of shaped like a seesaw if you think about it. Well, it would be if, well, I guess it is if you, I don't know, maybe you can picture a seesaw here. I struggle with it sometimes. But this is actually another case of 5 electron groups on a central atom having a shape of seesaw. Okay? In a case where now we have a second, let's see, yeah, ClF. I'm going to draw another case, which is chloride trifluoride, chlorine trifluoride, I guess. And this also has 5 groups, because, and again, I could take my time here, but I'm just going to zip through this because I've already spent a bunch of time. And I'm going to do some real problems where I throw an unknown compound up there and we actually sort out. We do the whole full Lewis structure and everything else, but here's going to kind of have an overview of the shapes. So in this molecule, it's shaped like a pair here and a pair here. Okay, that's right. And then all the fluorides are surrounded by 3 lone pairs as well. Okay, this shape they call T-shaped. Okay. There are again it's in this 5 group because there are 1, 2, 3, 4, 5 electron groups surrounding the chlorine atom. Okay, and again, this is another one of those cases where you see that this violates the octet rule. Here, the central chlorine atom has 10 electrons around it rather than the usual 8. That's okay because chlorine is at period 3. Similarly, well, never mind the example. I was going to come up with an example that says this is not possible, but but you know, but I won't. All right, and then last is the linear one, which yeah, I guess I'm going to skip that, but it's certainly possible also to have a shape that looks like this: a central atom followed by with an atom to the right and to the left, with a lone pair here, a lone pair here, and a lone pair here. Okay, and by the way, this is a common depiction in a lot of the books where they talk about shapes. Is they use the letters A, X, and usually E, I think, right? Yeah. Where in this case, what I'm depicting here is a central atom of whatever it happens to be that has 3 lone pairs around it, and it's connected to 2 other atoms on either side. Okay. This shape, it's one of these in the category 5, but the shape is linear because indeed it is linear. These electron pairs push these other to be as far apart as possible. Takes a linear shape. This whole thing is depicted as a molecule that follows the AX2E3 shape. Again, this is kind of a shorthand. It's the first time I've introduced this notation. A lot of books, our text uses it, and other things you'll see will say, some compound is an AX2E3, and this is just a shorthand for saying that it's a central atom with 3 lone pairs and 2 connected atoms. Okay. All right, and that's the last one for 5. And then very quickly, I'll do the 6th. I'm only going to do a couple with 6. The molecule I want to use is S-sulfur hexafluoride. I guess I got 6 there. And you can see there are indeed 6 groups around this. When you have, and the shape of this molecule is going to be octahedral. Okay. There are other shapes that happen when the molecule is when the pattern is instead of, this is actually a case of AX6, but there are other shapes for the when the 6 electron groups. So for example, AX5E, AX4E2, etc. Meaning the central atom has 4 atoms around it and 2 lone pairs, or the central atom has 5 atoms bonded to it and 1 lone pair, etc. And they form different shapes. It's in figure 10.8. 10.8. You'll see all the shapes from there. Okay. All right. I think that's all I wanted to do in terms of introduction of shapes. What I'm going to do next is I'm going to start to see. Is that right? Before. Yes. Good. I'm going to start to do a few problems, a few example problems that I think are going to be really indicative of what you're going to see on the exam, which is start with a compound. I'm going to pick a few, and I'm going to say, okay, let's write the Lewis structure for it. Let's see if there's multiple resonance forms. Let's do a formal charge analysis to make sure that we've got good forms, and then let's actually make a prediction of what the molecular shape will be. Okay, and that, by the way, will be the last one for chapter 10.